All right, so everyone's happy now, right? We're sharing our screen in Zoom. We're sharing our screen on the projector in the classroom. So we talked about trees last week. We talked about binary search trees. And one of the things that we mentioned is that in the worst case, what is the big O for finding something in a binary search tree? That would be the average case. That would be the worst case. That would be the typical case. Wait, did I say worst?
Yeah.
Sorry. That would be the average case. That would be the typical case, but it's not the worst case. Because in the worst case, with a binary search tree, you can end up with what's basically a linked list, right? Everything just goes down one way or the other, right? Or it doesn't even, I mean, it could be zigzagging back and forth, but just one, if there's just one node on each level, then you've basically got a linked list. And so your search becomes big O N. So the way that that we try to get around that is we have a variety of techniques or algorithms for keeping our binary search trees balanced. In this chapter in zyBooks, we're going to talk about two of those techniques. There's another one that we're not going to cover, which is in one of the chapters at the bottom. This is not used. It's called B trees. Less commonly used. So we're not going to cover it. I think you'll be fine with just having these two that we're going to talk about. So just to make sure that everyone's clear on the motivation here, we are trying to make it so that our big O for doing a search is not just typically big O login or average big O login, but worst case big O login. And the way we're going to do that is keep the tree balanced, right? Okay, so there we go. Apparently my audio was working. You know, in the past when I have used Zoom, I've always known when someone types something in the chat, but that doesn't seem to be the case when I'm here in this classroom. So, all right, so we're going to talk about something called an AVL tree. A binary search tree is considered height balanced if for any node, the heights of the node's left and right subtrees differ by only 0 or 1. So you take a look at, go through every node in the tree, look at the left subtree, find the height of that, look at the right subtree, find the height of that. If the heights differ by 0 or 1 for every node in the tree, then it is a height balanced binary search tree. Okay, so we'll do some practice with that. The other term we're going to have to be familiar with is the balance factor. So that's going to be the height of the left subtree minus the height of the right subtree. So in order for a binary search tree to be height balanced, the balance factor is going to be 1, 0, or -1. Okay. And it does matter, the direction does matter. It's not commutative, right? It's the height of the left subtree, excuse me, minus the height of the right subtree. Okay. So, and just to be clear, this gets a little confusing, so let's review. A tree with just one node has a height of 0. Right? So for purposes of the balance factor, we're going to say that a non-existent tree has a height of -1. Just to make it so that we can calculate the load the balance factor, even when the one of the sub trees is null point. Okay, so this is an AVL tree, right? Let's look at D. What's the height of D's left subtree?
1, 2.
Yeah, I heard 3 different answers. The height of D's left subtree is,
Oh, the whole thing is 2. 4.
so the D's left subtree is, whoops, just the C and the A, right? So remember, if there's one node, the height of the tree is 0. This is a tree that has 2 nodes, right? So the height is 1. So the height of D's left subtree is 1. Okay, so think of it as we're not counting the nodes, we're counting the branches.
Like the index.
Yeah, okay, I can see the similarity there, right? So the height of D's left subtree is 1, the height of D's right subtree is 0, so the balance factor is 1. So we're okay on node D, right? And so then we just go through and do that for every node in the tree. Hopefully after a while, we don't have to do it for every node in the tree. It becomes a little bit intuitive, right? But, C's left subtree is 0. C's right subtree is -1. 0 minus -1 is 1. So C's balance factor is 1. 0 minus, it says right here, right? 0 minus -1 is 1. That's the load factor. Okay. And then leaves obviously are going to have a balance factor of so if you've got a leaf, the left subtree has a height of -1. The right subtree has a height of -1. So the balance factor is 0. Okay. Any questions about why this counts as a binary search tree that is height balanced? Okay, so, and I guess, was this in there or did they just, is this kind of implied? Okay, an AVL tree is a BST with a height balanced property. Okay, so if a binary search tree is height balanced, that makes it an AVL tree. Okay, how about this one? And the answer is sort of given to you there, right? But you can, D is okay. D passes the test because the left subtree has a height of 2. The right subtree has a height of 1. E, hopefully you can look at that pretty quickly and notice that the difference between the left subtree and the right subtree is only going to be 1, right? Regardless of what the exact heights are and everything. This one has a node, this one has none. The difference is 1. Actually, it's going to be -1, right? I can't keep that term straight. The balance factor for E is 0. Oh, wait, yeah. Yeah, -1 minus 1. Wait. Now I'm getting confused. Okay, the left subtree here has a height of -1. The right subtree has a height of 0.
Oh, okay.
-1 minus 0 is -1. Okay. But if you look at C, the left subtree has a height of 1. The right subtree has a height of -1. 1 minus -1 is 2. Okay, so there's the formal way of looking at it, which is what you use maybe when you're first learning this or later on when you've got more of an intuitive sense for it, but then you just need to make sure, right? But hopefully you can get to a point where you can just look at C and you're like, okay, well, C has nothing on the right. And it goes down 2 nodes on the left. So it's not balanced, right? Okay, indicate whether each tree is an AVL tree. So I apologize for doing your homework for you, but let's just go through this. A
Yeah.
looks like it to me. So B is going to have a -1. A is going to be 0. So the balance factor. Do I have that? Yes, the balance factor, BF, is for B is -1. The balance factor of A is 0. The balance factor of C is -1. The balance factor of D is 0. I think we're good. How about this tree?
No,
No. How can you tell that just really intuitively quickly?
the E and the D, it's like going down more than once.
Right. So if you look at node C, there's nothing on the left. It goes down 2 nodes on the right. So it's not height balanced. Is that the word? Height balanced. Yeah, it's not height balanced. To be more formal about it, the height of the left subtree is -1. The height of the right subtree is 1. -1 minus 1 is -2. How about part C?
No.
No. Same reason, basically, right?
Yeah.
Part D?
Yes.
I believe so, yes. Okay. Part E?
Yeah.
Let's look at the 400.
Oh.
The height of 400's left subtree is
2. Or no, 1.
1. Okay. We'll get this. The height of 400's right subtree is
0 or -1.
-1. 1 minus -1 is 2. So part E, the answer is no.
Don't we need to take into consideration the right side of the pipe? Wouldn't that balance?
Yes, but if you find a single node that doesn't meet the requirement, then it's a no for the whole tree.
Oh, okay.
So in order to be an AVL tree, every node has to meet the requirement.
So 500, the root meets it, but the first. That. does
Right.
not meet
The
it.
400 doesn't meet it and the 600 doesn't meet it. Good. What about F?
Yeah.
That looks good to me. Uh-oh. Oh, because so it's not a binary search tree. It meets the height requirements, but trick question, right? The 99 goes the wrong way. All right, getting the basic idea. So does this guarantee that there aren't going to be any kind of sparse areas in the tree? That's a very ambiguous question, right? I'm not looking for right or wrong here. I just want to think about that for a second. So when you think about a balanced tree, your initial instinct might be like the number of nodes on the left and the number of nodes on the right are similar.
Yeah.
Right? Or it's kind of full, or maybe not technically full, but kind of full, right? That is not necessarily the case in an AVL tree. I haven't taken this challenge, but conceivably you could write something that meets the AVL tree definition, but it's missing quite a few nodes. Okay, so there's no guarantee that this is actually log base 2 of n, but it has been shown that in the worst case, it would be about 1.5 times log base 2 of n. So just the number of nodes is not going to get anywhere near n, even though it might not be a perfect log base 2 of n. Okay. So the deal is that in order to keep this AVL tree requirement, whenever we do an insertion or a removal from the tree, actually turns out to be a pretty low number of moves are required. We can keep it balanced with just 2 or 3 assignment operators assigning pointers every time we do an insertion or a removal. Okay, and the way we do that is going to be with something we call an insertion. So actually, here's what we were just talking about. I got ahead of myself a little bit, right? Theoreticians have shown that an AVL tree's worst case height is no worse than about 1.5 of the minimum binary tree height. The minimum binary tree height being log base 2 of n, right? So here's an example of an AVL tree where it looks like there's some missing nodes, right? It doesn't look very full. An AVL tree maintains the minimum possible height. True or false?
I want to say false. Yeah.
This tree right here,
Yeah.
right? The minimum possible height on this tree would be 2, but this tree has a height of 3. AVL tree with a height close to the minimum. So false. What's the minimum possible height of an AVL tree with 7 nodes? That's not really even about AVL trees, right? Just about trees. Binary trees. Minimum height 2, right? Here's the picture right here. What's the maximum possible height of an AVL tree with 7 nodes? I'm not sure that was actually discussed, but I'm going to guess that we're not going to be able to make it 4.
Yeah. That's it.
I'm not sure, like if we take the 19 away, then 37's left subtree is going to be too small, right? If we take the 98 away and put it down here, then 72's right subtree is going to be too short. So I'm gonna say the maximum possible height is probably going to be 3. What do you think? Yay. Oh, look, it was using that formula that they gave us. Okay. One possible implementation of an AVL tree is that you store the subtree height as a member of each node. That's pretty common, right? Because otherwise, every time you need to move something around, you have to recalculate the height so that you know that you're keeping it balanced. So every time we do an insertion or a removal, we're going to have to recalculate some of the heights that are stored in the nodes. With the height stored as a member of each node, the balance factor for any node can be computed in big O 1 time. Just subtract the 2 heights, right? We need the height recomputed. Okay. Don't think there's anything too exciting here, right? So here's a tree. If we insert 55 into this tree, it's going to end up down here, right? And so what we're going to have to do is we insert the 55, we set the height, and then we're going to have to go back up the tree, adjusting each node in the hierarchy up to the root. Because those are the only node. If I insert the 55 here, like is normally where I would put it in a binary search tree, the only heights that are going to change are ancestors of that node we just added.
So that wouldn't increase the big O though? Going back through.
Well, so the insertion, so what's gonna be the big O of that process of updating all of the balance all of the heights in all of the ancestors? What's the big O? Log in. So every time we do an insertion, it's already log in. So having to update all of the ancestors' heights is gonna make it 2 times log in, which we don't care about, right? Because 2 is just a constant. Okay with that? Okay. And if it's updated, the balance factors can be computed on. I mean, okay. I think we're good there.
When they're counting the height kind of backwards in this, like we're used to counting the root is height 0, right? Or is that level? Am I getting level and height?
Yeah, I think you're getting level, right? That's level.
Okay.
Right, we haven't really talked about heights of nodes before, I don't think.
Okay.
We talked about the height of a
Tree.
tree. The height of a tree was the length of the longest path. That's how we define the height of a tree. So now we're basically saying the height of all of these subtrees, right? Okay, yeah, so height hasn't really been much of something we've talked about much. All of a sudden it's becoming more important. What relationship does a node's height have to the node's balance factor? Is the height going to be equal to the balance factor? No. A negative height would mean that it doesn't have a node.
Yeah.
There isn't a node, right? A node can't, in other words, a node can't have a negative height, right? So we can stop reading right there. Absolute value of balance factor equals height. I mean, I think there's really no connection, right? I mean, you could have a tree with 1 million nodes in it. The height of one of those nodes could be 30,
Right.
but the load factor could be 0.
Sure.
Right? So I think the answer is here. Okay. Kind of a fun puzzle, I guess. Okay. When adding a new node, what is true about the order in which the ancestor height values must be updated? Height values must be updated starting at the node's parent and moving up to the root. Must be updated starting at the root, moving down to the node. Could be top down or bottom up, or could be just any random order.
Probably starting at the root, just
Starting. We said starting the parent. Move up to the root.
Yeah, I think I actually gave this one away. When we add the 55 down here, can we immediately then go and update the height of the root? I mean, I suppose technically you could say, then go to the root. Well, but then you don't know which way to, no, because you could go to the root and then start back down the path, just adding 1 to each node, I guess. It seems very counterintuitive.
Yeah.
Seems
how
much.
do you traverse back up? There's no pointers to the previous.
All right, so maybe you insert this and then you don't have a pointer to the node, to the root. I mean, I suppose you could just send that as an extra parameter or something. You could make that work, I think. But it's much more intuitive to just start where you inserted the node and then just work your way back up, right? And my guess is that's what the answer is going to say. Watch me be wrong. Starting at the parent's node, moving up to the root. Yes. since the height values require, I think that's supposed to be singular. Oh, no, since updating the height values requires child node heights to be updated. Oh, right, because, okay, good point. Because, so we can't start at the root because we don't know what the height of the left subtree is. What if the height of the left subtree is 17? Then the height of the root doesn't change. We don't add one to it.
Yeah.
So we add the 55, we insert the 55, then we look at 55's parent, and we look at, so we're looking at the 76. We look at the 76 left subtree's height. We look at the 76's right subtree's height and set 76's height to 1 plus whichever's bigger. Right? So if the 76 has a subtree over here to the right with a height of 17, inserting the 55 right here isn't going to change the height of the 76 node. It's still going to be 17, 18. Right. So it is the case that we must start with the parent of the node that we just inserted. Good enough?
Does this require a
Yes.
member that will point to the parent?
Yes. So in order to make this stuff work, we're going to have parent nodes. Parent pointer. Yeah. Okay, that was actually a good question. It made us think through this a little bit, right? When would inserting a new node to an AVL tree result in no height value changes for all ancestors?
That case you just talked about.
Probably, yeah. The new node is inserted as a child of an internal node with 2 children. That's not possible. If an internal node has 2 children, then the new node wouldn't be inserted as that node's child, right? A new node is inserted as a child of an internal node with 1 child.
Probably right there.
Yeah, because if there's 1 child, that means that either the heights are the same now, or the height of the other subtree was already larger. And so adding 1 in the other direction isn't going to change it.
I guess it can't be too much larger, else it wouldn't be a balanced tree.
True. Yeah. But I think that's it. A new node is inserted as a child of a leaf node. Not necessarily. No. Okay, so I think it's this guy. All right. Okay. How we doing? Let's play with this a little more. I think this is the last one for this first section. So basically what we haven't talked about yet is how do we fix it when we insert a new node and it unbalances the tree, right? So that's sort of where we're heading. We're setting the groundwork for that first. But let's play around with this a little bit. What is the height of 80? It's not letting me do
We
it.
don't just start,
Oh, duh. I still forget to do that. What is the height of 80?
Yep.
Oh. 80's left subtree height. 80's right subtree height. Got it. 40's left subtree height.
-1,
40's right subtree height.
1, or 0.
Yeah.
So
40's balance factor. -1. So it's -1 minus 0. -1. Right? Okay. Is this an AVL tree? I believe so. Is this an ABL tree?
No,
No, because of which node? 50. 50 has an invalid AVL balance property.
Isn't it because of the ordering? 50, 70?
I think the ordering is
That's ordering,
correct.
But isn't the left tree's height? Oh, it's negative. So
So-
negative 1 minus 1, so it's negative.
Right, yes, -1, yeah.
Okay.
This one?
Well, out of order.
Right, it meets the AVL balance property, but it doesn't meet the BST criteria, right?
Yeah.
Because of the 60 here. Violated by 50 and 60. Right. How about this one?
Balance.
Not balanced. Because of which node?
50.
50. All right, you guys are on it. Let's just, I can't resist finishing it up since we're so close. After inserting 60, what is the height and balance factor of the 70? So where's the 60 gonna go? To the left of 70. Everything's still gonna be an AVL tree at that point. So what is the height of 70?
Yeah.
1, right? And the balance factor will be 0 minus -1. 1. After insertion, is the tree still an ABL tree? We already said. Okay. One more. When you guys do this, it'll be different, right?
Yeah.
Yeah.
Oh, yeah. I don't.
Okay. Consider the following AVL tree. So it's telling us already that it's an AVL tree. After inserting 60, what is the height of each node starting from 60's parent and going to the root? So we added 60 down here. So what will the height of the 70 be? Wait, list of node heights. So 70 will have a height of 1, which it already has, right? 50 will have a height of, whoops, 1. 50 will have a height of 2. 30 will have a height of 3. After insertion, is the tree still an AVL tree?
I don't think so.
I think it,
Is it? Yeah.
I think it is. Anybody find, can anyone find a node that doesn't meet the requirement? I'm gonna go with yes.
Yeah.
All right. Okay. All right, so that's the introduction to ABL trees and sort of what it means to be balanced, what it means to actually meet the definition of an ABL tree. Let's talk a little bit about rotations. So here's your first ABL rotation. You can rotate right or you can rotate left. In this picture, we're rotating at the 86. Not possible to rotate left. In order to rotate left, your node has to have a right child. In order to rotate right, your node has to have a left child. Okay, so we're going to rotate right, and it just means the 75 it's like I'm picking up the 75, right? And putting it up to the root, and it's going to have the children are going to be 30 and 86. Okay, so not an ABL tree. Do this little rotation to the right. Now we've got an ABL tree. Right, so you can imagine, I mean, I don't want to go too quickly to the code here, because just getting the rotations right is challenging enough. But just to, just think about it really quickly, you're just gonna make it so that 75's right subtree is the 86. And 86 no longer has any children. Right? What's going to be interesting is when 86 does have children. We'll get there. So rotating is said to be done at a node. Above the rotation is at the 86. Rotate right at the 89. I think this is pretty obvious what's going to happen, right? The 32 is going to be the root, 89 over here, 17 over here. So basic rotation, I think not too bad. If node 75, okay, here's where it gets a little tricky. If node 75 had a right 75, up here. If 75 had a right child node, what would we do with that? We can't just, so 75 is going to get a new right child of 86.
Would it be 30's right child?
Can't be 30's right child because it's going to be bigger than 75, right?
Right.
So if the left child, if you're doing a right rotation, the left child has a right child, that right child is going to become the left child of the new root's right child. Okay. I mean, once you draw the picture a few times, I think won't be that hard, but saying it is really hard. Okay. That makes sense though? If 75 had a right child, you'd pick up the 75, but whatever 75's right child was, you're going to stick it on the left of the 86. And that's including if 75's right child was a huge big subtree, right? You just make the 86, the 86's left pointer point to it. And 86 is going to have a left pointer available because the 86's left pointer used to be pointing at the 75. Okay, so hopefully we'll have some pictures of that, right? So here's exactly what we were just talking about. We're picking up the B, so it's going to have a left child of A and a right child of D, and this C hanging out here is just going to become the left child of D. So let's stare at that for a sec. Are we good? Okay, that's the rotation. The only difference is that sometimes instead of a right rotation, it's going to be a left rotation. So, if D had a right subtree, but not a left subtree, then you'd have to do a left rotation, right? And then the only other thing we're going to find out is that there's going to be some situations where neither a right rotation nor a left rotation is going to work. And we have to do left then right or right then left. We have to do a double rotation, but it's still the same rotation. You're just doing it twice. So the rotation we just learned, you may have to do it from the opposite direction. You may have to do it twice, but that's the rotation. Rotate the right at the 53. I think we've got this by now, right? We're going to pick up the 27. So the left child is going to be 9. The right child is going to be 53. The 29 is going to be down here, right? So 29 is going to be in 4. Yeah. Good with that? Okay. Isn't this cool? Kind of fun, right? I mean, I hope I understand sometimes things are terrible when you don't get it, and then once you get it, they're fun. Okay, so just make sure you get it because you can do it. It's not that hard, and then it will be fun. Okay, we're gonna rotate left at the 51. So we're picking up the 60. So the 60 is gonna go up here. 51 is gonna be the left child. 73 is gonna be the right child. And this 57 is gonna become the 25's right child, right? So the 57 is gonna be at N5.
It'd be the 51's right child.
51.
Oh, yeah, okay, right.
Yeah.
Yeah. So we,
51 is then 2.
right, 51 is into. Because we're picking up the 60. Picked up the 60. 51 is on the left. 73 still on the right. So 60, 51's going to be on the left, 73 is going to be on the right, 25 is going to be on the left of 51, just like I was before. The 82 just stays where it was, right? We picked up the 60, you put it here, so the 73 and the 82 stay.
Okay, so are we gonna need to use this process when the tree is no longer balanced? Is that-
Correct. Right. So, well, we'll get to that in a second, okay? But whenever we insert or remove a node, we're gonna have to go through a process of making sure that all of that node and all of its ancestors are still meet the requirement of being an AVL tree. And if we find a node that doesn't, then we do a rotation at that node. And I think we just have to go when we insert something, we just go back up the tree to the root and check all of those nodes, because it's not going to mess up anything else in a different part of the tree. Right? Yeah. Okay. I'm not going to talk about these. So now we're getting into some code, right? And let's just stare at it for a second. So rotate right. I don't know what this means. Left, right child gets node arrow. Okay, I get it. So node arrow, left arrow, right. So we're rotating right at D. So we're just setting left, right child equal to is going to be this C, right? And why do we need to remember the C? What's going to happen with the C when we do a right rotation?
Swap sides.
Right. It's going to become D's left child. Everyone okay with that? Okay. So we're going to remember the C. If node arrow parent is not equal to null, ABL tree replace child, node parent, node arrow left. And we're gonna, I'm kind of waving my arms a little bit on the code for now. Okay. Apparently, in order to understand this code, we would have needed to study these in more detail. But I'm a little excited about getting to the double rotation. So right rotation algorithm. Okay. I'm waiting for double rotation to come. So this is basically what we already talked about, right? We start with this tree. If we're going to insert an A, now it becomes unbalanced. So we're going to have to do a right rotation at C because that's the node that is not balanced, right? So we're going to pick up the B. Right? That's basically what we're already talking about. Okay, sometimes the imbalance is due to an insertion on the inside of a subtree rather than on the outside. So far, every time we've done a balancing thing, it has been either because we had too many nodes going down the left or too many nodes going down the right. So now the question is, what happens if instead of adding A on the left, we added A on the right? And we want to do a rotation at C. So we start with this. We add B on the right. We try to do a right rotation at C. Still imbalanced, right? So what we're going to have to do is we do a left rotation. Oops. Yeah, that's the same thing. First rotate left at C's child, so that we end up with basically the situation where we're inserting to the left or on the outside. And now we can do a right rotation and we get a balanced tree again. Okay. So if the insertion is on the inside of the tree instead of on the outside of the tree, then we have to do a double rotation. If it's on the left side of the tree and we insert to the right, if it's on the left side of the tree and we're inserting to the right, then we're going to rotate left first and then rotate right. And when we rotate left, we're not rotating at the node that has the problem. We're rotating at that node's left child. All right. So lots of stuff to remember. But I don't think any of the individual things to remember are actually all that hard. Just a lot of stuff. Right, so this is basically the bad situation right here. We're inserting bad, meaning we're going to have to do a double rotation, right? So okay, after the initial left rotation, so because we're inserting on the inside of the tree instead of on the outside of the tree, we can't simply do a right rotation. We're going to have to do left rotation at X first, and then do a right rotation at Z. So the left rotation at X. After the initial left rotation, where is Y?
So one child of X.
So
Oh, yeah,
Or
yeah, and 4. But I thought it was pretty soon.
So we're doing a left rotation at X,
Oh,
which means we're going to pick up Y, and Y is going to become the new root, right? So Y is going to be at N2. And then X is going to be at down here, right? In 4. Okay. Then after the left rotation, where is the right rotation performed? At Z, right? At the original node that was problematic. Okay. After the left rotation and then the right rotation, where is Z? So we got Z, Y, X. And now we're gonna rotate at Z.
Z gets to N3.
Z goes down to N3, right? And where's Y at that point?
Oh, no, yeah, and
Y was here. To do a right rotation at Z, we're picking up Y. So it becomes N1. After the left rotation and then the right rotation, where is X?
And
N2? If the left rotation had not first been performed, a right rotation at Z would have made X the new root and made Z X's right child. So right rotation at Z, we pick up the X, Z becomes X's right child. What happens to Y? Becomes Z's left child, right? So Z is asking about Z. No, let's see. It's asking about Y. Y would be at N6. Should I do that again?
yeah,
Let me make sure I'm right first. N6. Yeah. Okay. So rotating right, I'm going to pick up the X. So the X goes into N1, the Z goes into N3. And remember, if we're rotating right and the left child has a right child, that right child ends up being Z's left child. That's probably the trickiest part right there, I think. It's also almost the very first thing we talked about. But any questions about any of that? Okay, so basically the you can divide this into 4 possible cases, right? You're adding something to you're inserting something at the problem node's left child. You're adding something at the problem node's right child. You're adding something at the problem node's right child. You're adding something at problem node's left child, right? These two, the second one and the fourth one, require double rotation. So for example, this one, the insertion is on the right side of the tree, so I have to do a right rotation at the 46 before I do the left rotation at the 37.
there will never really be any more filled in than that, because if it is, then it's not violating the balance tree. Like there's not gonna be other.
Right. You can't have the 23 can't have a left child. Yeah, I might have to work through basically, yes, you're right. I'd have to think hard and work a little bit to actually prove that.
Right, no, but I'm just trying, yeah.
So you don't have to worry about the 23 here having a right child or a left child here. Because if you insert a left child at the 23, that is not going to make the 51 be out of balance.
oh, right, okay.
Well,
Or
I should rephrase that. If the 23 already had a left child, then inserting the 38 would not make the 51 go out of balance.
you would never be at that point to begin with without either rotating first or it being in balance, right?
Okay. All right, so I'll let you study this in some more detail. I mean, this is the sort of thing where, you're really going to just have to set some time aside sometime and sit and stare at it for a while. The project, if I were to just talk about it for a second, I would say. Honestly, you don't really have to be an expert on the rotations. To do the project. The project is gonna be more about. I'm not sure how to say it. Here's what I would say. There's not a ton of code. It's hard, but there's really not that much code. You have to sit and stare at it for a while. So that you know exactly where the code goes that you need to put in it. But the number of lines of code is very small, actually. And, you know, it's the type of thing where you could throw a couple things in there, and if they're wrong, you probably don't want to just try to fix it. Because you're just like, you get started down the wrong path and it's not going to be pretty. So, yeah. And same thing with this, if someone just emails me to remind me, I think I can give a pretty big hint on it. If you want me to. All right. Anything else before we go? Not planning on being here Wednesday, so we're looking at next Monday. We'll talk about heaps next Monday. We'll talk about, here, give me a sec. Where did that go? So next Monday, we'll talk about heaps. The Monday after that, we'll talk about graphs, and I think I'll be pretty much done. Because so the 27th and the 4th, I probably won't do meetings. So 2 more. All right. Okay. I will see you next Monday.
I have a quick question about it. The program that's there today, is it fine if I'm using namespace standard in the header, or should I? Because I need a namespace standard for set, so I didn't need to do the,
You should use std::: instead.
okay.
Not that I would probably notice that, but that would be the right thing to do. Yeah,
Oh, what's in the APL standard?
I have no idea. That's a great question. Automatic vehicle locator.
No.
You don't think so? Encoding. Named after its inventors, Adelson, Valsky, and Landis. So the other kind of tree that I didn't have time to talk about, so you'll just have to work it out. But I think the Zybooks is pretty awesome for learning this particular subject. But the red and black trees are how the STL implements a couple of the standard template library classes. So it's actually, you know, the real deal, right? Can't remember what it is. I think it's set or multi-set or something. All right. See you next time.